Greetings everyone, welcome back into trigonometry. Time to take another side step for a moment to finish up Unit 2. We're going to talk about a test that I've given in the past for the topics in Unit 2. And it may seem kind of short because the list of topics is short, but this is one of those things where these are important topics that need to be practiced a lot more. So we're hitting the graphing on all 6 of the major functions: sine, cosine, secant, cosecant, tangent, cotangent. Simplifying inverse trig expressions is a multifaceted skill as well. There's 3 different types of those problems. And then the advanced applications are anything from bearing to repetitive motions. So just as before, remember, this isn't something that you want to memorize these individual problems, but hopefully watching me work this test will give you some insight into generic procedures that you should practice and get used to following. So let's start this adventure off with some graphing. We're going to graph 2 periods of each of these functions. Let's start with the y equals tangent 8/9 x plus 1. Alrighty, so let's categorize here, right? Remember, the 8/9 x is actually what's being acted on by the tangent here. So the 8/9 is acting as my quote-unquote frequency here, right? That's my b value that's in front of x. So from there, I know for tangent, I can calculate the period as pi divided by this 8/9, which is going to give me 9 pi over 8. And then also remember, the plus 1 is a shift up. Okay, so those two are unrelated. The period is going to stretch or compress it in the horizontal direction, and the plus 1 is going to shift it either up or down. In this case, up, right? Because of the plus 1. So I've got my period is 9 pi over 8. And remember, since I'm doing this by hand, not on the computer, I'm going to actually put down my own marks, which means it's easiest to do with quarters, right? So I need my quarter period. My quarter period is 1/4 of p, which is going to be 1/4 times the 9 pi over 8, which is going to be equal to 9 pi over 32. Okay, so I've got my quarter period here. And remember, if you are doing this on a computer and they're giving you the pre-made marks and things like that, it's okay to still figure out the quarter period. You can count by quarters, and if you need a half, just do 2 quarters, or if you need a whole, just count all 4 quarters as one jump, or you know, whatever you need to add can still be done in quarters. That's the beauty of it. Okay, so let's go ahead and throw down my x-axis here. I need 2 periods, so I'm going to stick to this left-hand side first. I'm going to go ahead and put my first 5 marks. 3, 4, and 5 here. Okay. So from here, remember, tangent is the one oddball, right? He's the one that stands out different from the other ones. Tangent starts at the center of your period. These 5 marks represent my first period, okay? And my asymptotes are going to be on the first and the 5th marker. My center, the thing that gets shifted for tangent, is in this middle mark. If it were cotangent, I would have started here on this end, but here, that's this one. Now, what's nice about this is I don't have a left or right shift, so this is automatically 0, right? Which also means that this is my y-axis here. Okay? And then for another period in a minute, we'll do 5 more marks. Okay, so then my quarter period is 9 pi over 32. That means this should be 9 pi over 32. Because each quarter is that length and I'm starting from 0. So then the next one should be 18 pi over 32, because I'm just adding another 9 pi over 32. And yeah, you could reduce that if you want, but remember our whole goal was counting it out here. So this should be negative 9 pi over 32, and this should be negative 18 pi over 32. I do need to put my asymptotes there. So let's do that. My vertical asymptotes are here and here for the first period that I'm graphing. And don't forget, you can always go back and check to see, right, by plugging it in. If I plug 18 pi over 32 into here, right, 18 pi over 32 times 8/9 would give me, let's see, this is 9 over 16. And so the 9s would wipe, and 8 over 16 would give me 1/2. So it would give me pi over 2. Tangent of pi over 2 is undefined, hence the asymptote. So don't forget, you can always plug these back in to double check. Hey, does that give me an undefined value? And it should. Okay, then the only other thing I have to worry about is the plus 1. So I'm going to put plus 1 here. And then I'm going to take that same length and count up to 2. And remember, the reason is because my amplitude is 1. Okay? On a tangent, the amplitude doesn't matter as much. I still want you to label it. Okay? So then I can go ahead and draw my first cycle here. The center is going to be here, right here. It was just shifted up 1. And then tangent increases. Tangent goes up. And it's not reflected or anything like that. So I'm going to be going this way, right? Up this way. And so to have an amplitude of 1, that means at the quarter mark, I'm going to be down from the center by 1 value. And at the other quarter mark, I'm going to be up 1 from the center. So then my graph should look something like this. And of course, I know it's kind of real, flat and instead of like, it's real stretched out instead of being more flat in this case, right? But you get the idea. It's doing the correct motions in the correct direction and hugging the correct walls here. That's the main point. Okay, so then to do a second period here, I'm simply going to put 5 more marks, but I think I'd like to have a straighter x-axis. I should have used my straight edge on that one. Let's see if I can do a little better. That's a bit better. All right. 1, 2, 3, and 4 more marks. Those are a bit differently spaced. Oh well, we'll get over it. Okay, I'll need 1 more asymptote here at this end, right? Because every cycle begins and ends with an asymptote if you start that way. Although technically we started at the center. Okay, and I'm still counting quarter periods. So 18 plus 9, I have 27 pi over 32. 36 pi over 32. Then 45 pi over 32. And finally 54 pi over 32. And then the graph should repeat, right? Because it's a second cycle of the same thing. So I should be going through this point, and this point, give or take. Something like that. Okay? Now remember, the importance here is, did you get the correct orientation? Did you get the correct asymptotes? And can you identify certain points if asked to? Sure. Like, for example, this point right here, one of the amplitude points. We could definitely identify that as the point 45 pi over 32, comma, 2. that this graph definitely goes through. Okay? So things like that tell you whether or not your graph is going to be correct. Not necessarily did you get the perfect shape or anything like that, but can you get that meaningful information out, and does the graph have the correct shape and direction as far as the way it's supposed to look, like which wall does it hug, and is it increasing or decreasing, and things like that. Okay, next. Oftentimes on my tests, to save space and thought time, I'll put a cosine and a secant, or a sine and a cosecant together on one problem to be graphed in the same grid. And that's because to graph a secant, I really pretty much am graphing a cosine anyway, since they're reciprocals, right? That's how we typically graph the secant and the cosecant, is by graphing their reciprocal, cosine or sine, that goes along with them. So I tend to just say, okay, well, show me both of these, and you just draw them both on the same grid, because you're going to probably end up doing that anyway. Okay, so let's break it down. I'm going to start by dividing the 3 pi out, basically factoring it out to make it easier to read the shift. I'm going to divide by 3 pi like this. So it'll just be x minus 12 pi divided by 3 pi is just 4. Okay, so I've rewritten that one just in a more factored format. Some people prefer not to factor it. Some people just prefer to say, oh, the 3 pi here is the frequency, and I can create the period from it, which we still are going to do that. And then they also like to think of it as, oh, what's the negative b over c, to just calculate the shift. Personally, I like being able to see the shift, but if you'd rather do the b divided by c and find your shift that way, that works just as well too. Okay? Now, let's talk about the period here. The period is going to be the same for both, right? Because they're bouncing off of each other anyway. The period is going to be 2 pi. Remember, that's for sine and cosine. They use 2 pi, whereas tangent and cotangent is just pi. 2 pi divided by the b number, which in this case is 3 pi. So my period is 2/3. Okay, so let's do the quarter period. Quarter period is going to be 1/4 times 2/3, which in this case is going to give me 1/6. So there's my quarter period. However, I now also have a horizontal shift. And remember, that is going to be affecting with the period here, right? This is going to be a shift right. So then when I'm making my marks, I need to make a mental note and then eventually an actual note that this is in fifths, and the quarter period that I'm counting the marks with is in sixths. Okay? So I'm going to need a common denominator here between those two. 30ths, right? So let's go ahead and mark that out. 1/6 is the same thing as 5/30ths, right? I'm going to need that. And 4/5 is the same thing as 24/30 for my shift right. And then the only other thing to worry about here is, of course, the amplitude, right? My amplitude is 2. And that's just going to be our high and low on our cosine, and then the dip for the secant. Okay, so here we go. I'm going to do it right this time. We'll go ahead and get a straight edge on here. All right. So give or take, go ahead and put an x-axis on here. And we'll do a mark every 2 inches. That ought to give us plenty of space. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, that's plenty of space. I'll go ahead and finish out what I have marked here, though. All right. So let's label our marks here. I know that I'm starting with a mark that is positive, okay, because it was shifted to the right. So you know what would be better to be able to find my y-axis on this grid? I'm not going to put my first mark over here, okay? I'm gonna count a few marks over this way. In fact, maybe even just go 5 this way. 1, 2, 3, 4, 5 this way. Let's do 6, 7. Let's make it a few marks here. I'm going to put my my first mark somewhere right here in the middle. And not because it's like tangent or anything like that. Just imagine I had put my 5 marks just right here. Okay? I know that my y-axis is going to be over here because my shift to the right is positive. 24 over 30 here. So I know my y-axis is over here. I may as well take advantage of that fact and that I have to do a second period, a second cycle, and count this way instead of just counting strictly to the right. Okay, so now this is where my beginning point is going to be for everything. I'm now going to start counting 5/30ths in both directions. So this will be 29/30ths, right here. This one will be 34/30ths. Then I'll have 39/30ths, 44, 49. 1, 2, 3, 4, 5. Okay, that's pretty far. Now I'm going to do minus, so this will be what, 19/30ths, then 14/30ths, then 9/30ths, then 4/30ths. Then I'll have -1 over 30, -6 over 30, right? And then finally -11 over 30 is just I'm just labeling the marks that I have, all the while keeping in mind that this is actually where I'm starting my first cycle right here. Okay? 54 over 30, 59 over 30. Probably many more marks than what I need, but I happen to just have that much space, so I'm just counting it out. Okay, well, I also was able to find my y-axis, wasn't I? Right here, in between the -1 and the +4 has to be the y-axis. Probably a good bit closer to the -1, I would think, than the 4. Right? This would only be 1/5 of the way versus 4/5. Okay. So let me just cap that one. Try to keep this thing straight. Nothing's ever perfect, but you know, it's nice to see a good line to be able to do these graphs in a nice way. That'll do. So there's my y-axis. On a test paper, you know, you could use your ID card or the side of your calculator or whatever. I just happen to have a ruler here. Okay, and for my amplitude, right, I need an amplitude of 2. So I'll just go ahead and put a couple of marks on here and label them. So I've got -1 and -2 here. And then this is still -1 over 30. I'll just draw it a lot smaller there for the sake of the axis. Okay, so now we're ready, right? We are ready to draw this graph. Okay, so I'm doing the cosine, which means at this beginning point, it has to start at a peak. Okay, so that's going to be right here. And then the first quarter should be in the middle. The second quarter, or the halfway, should be at the bottom peak. Then back to the middle, then back to the top again, right? Give or take some space here. So I should have something that looks like this. And I know on the test paper you may not have, multiple colors. You can do one of them dashed and one of them solid, but you got to be careful because your asymptotes are dashed too. Okay, so here's one piece of the cosine. Let's go ahead and do another one. I'll come back towards the axis here. I know that it's at the peak here, so then it's going to have to go through the bottom, through the middle, then the bottom, right? Close enough. Then through the middle again, then back at the peak again. So something like this. Okay. And then, of course, it's going to hit on through here and just keep going. Same thing over here, right? It's gonna hit through here and just keep trailing on from there. So I've got two periods of the cosine now. Let's throw up the asymptotes for the secant. Remember, secant is going to be undefined anytime cosine goes through its own center line. Well, we didn't shift up or down, so the center line is the x-axis, which means I have asymptotes at 9/30ths. At 19/30ths, at 29/30ths. I hope you're seeing a pattern here. 39/30ths. Let's see. Up, down, up, down, up. That should be. Let me go ahead and put this one in. As long as we have two ups and two downs, then that's enough to call it two full periods. Okay, so let's see if I've got a good enough color here. How about this off magenta again? So then my secant is going to be hugging the walls and kissing the peaks, right? Like this. And then like this. And I've already drawn two cycles there, but I'm just going to keep on doing what I got here. Okay, that's good. So there's my secant. Let's take a quick look at the two graphs that I just drew by hand so we can get a really fine-tuned look at them here. Notice this is the tangent 8/9 x plus 1, and the shapes are pretty self-explanatory. You can see where I have the amplitude marks at 1 away from the center, right? Here's the first center point is right here. The first center point is there, the one that was shifted up. Then you can notice that there are quarter marks for the graph at those 2 points where they're 1 away from the center, and notice they are actually at the quarters there. And it's the same each time. You've got the center and the quarters on either side for all of the cycles there. Okay, and next you can also notice that there is an asymptote at 9 pi over 16 here, at 27 pi over 16 here, at negative 9 pi over 16. And it actually simplified its fractions. Of course, on our graph, we drew that as the negative 18 pi over 32 and the positive 18 pi over 32. Okay, let's take a look at the other two graphs. Here are those two on the same grid. The green is, of course, the cosine, you can see here. The blue is the secant. They are, in fact, the same period and shift and everything. And you can tell where the shift was originally. Here's the 4/5 shift, which is that peak on the cosine there. That was our original shifting mark. Note where the asymptotes are. I have 29 over 30. I have 19 over 30. And technically this is 9 over 30, but it reduces to 3/10. And then the -1 over 30. Those are examples of where my asymptotes are. And notice it's always where the cosine goes through the center. And then, of course, the secant at each spot is hugging the walls and kissing the peaks, as we expected. Next, let's tackle the different types of inverse trig operations that we need to be able to simplify. So in this test, I assigned these three problems to go at the different facets of using an inverse, from just simply doing an inverse all the way through mixing the different trigs with different inverses. Okay, so let's start on this end right here. Notice I wanted them to calculate or simplify, and only exact answers are allowed in radians. Okay, so inverse sine of negative square root of 2 over 2, if you were to punch this in the calculator in radians, it's not going to give you the exact answer. It's going to give you a decimal. Okay, for the calculators that we're allowing them to use. So you need to know your stuff on this one. You need to know your memorized values. Okay, so right here, notice that what this is doing is it's asking for a couple of pieces of information that you need to notice. The first that you need to notice is that this is an inverse sine associated with a negative. And remember, inverse sine is defined for two quadrants only on default. It gives quadrant 1 angles as an answer if it's positive, and it gives quadrant 4 answers if it has a negative. And remember, it doesn't just give the quadrant 4 normal, it's going to give it as a negative acute angle. Okay? So the sine mixed with the negative is telling me that I need a quadrant 4 negative acute. Okay? That's the piece of information that I'm seeing there. Now mix that with the other piece of information that we see, which is the fact that I have a sine associated with the square root of 2 over 2 ratio. So in your head, you should be thinking, well, I know that sine of 45 degrees is square root of 2 over 2. Therefore, 45 degrees is your reference angle, right? But we're doing radians, so I need to convert that. This piece of information is telling me that my reference is pi over 4. So I have this reference, and I need to give a quadrant 4 negative acute angle. Okay? So in this case, since I have to show graphs to support my solution, I'm just going to be drawing simply the fact that I'm going to be using negative 45 degrees here, and it's going to give me the appropriate square root of 2 over 2, because I can count this like 1 and 1 and square root of 2. Okay, or technically this is -1 right here. So here's the solution. Inverse sine of negative square root of 2 over 2 is negative pi over 4. Next, arc cosine of the cosine of 11 pi over 9. Okay? So here's the thing that I'm trying to see if you're paying attention to. Can I just cancel these out? Can I just wipe them away because they're inverses? No. Remember, there's stipulations on these, and only certain times allow you to just wipe them out. And this is not one of them. Cosine, and specifically arc cosine, inverse cosine, is only defined for quadrants 1 and 2. Well, 11 pi over 9 is not in either of those, so I can't just wipe it out. I need to consider that 11 pi over 9 is in quadrant 3. Like so. So then what would the reference angle be? Well, remember this is pi right here, right? So if I do 11 pi over 9 minus pi, remember pi would be 9 pi over 9. I would have a leftover 2 pi over 9, right? So that would be this angle here would be 2 pi over 9, my reference angle. Okay, next, you need to assimilate that this is quadrant 3, right? This is quadrant 3, which means cosine is negative. Cosine of theta is equal to a negative number. So that means that I'm doing the inverse cosine on a negative number here. Remember, inverse cosine is defined for two quadrants, quadrants 1 and 2 only. And if it's acting, arc cosine is acting on a negative number, that means I should be giving a quadrant 2 answer. Okay? So, with that in mind, I take this reference angle of 2 pi over 9 and I convert it to a quadrant 2 answer. This is my original reference angle for what was given, and I'm recreating it. I'm repurposing this angle right here, 2 pi over 9, so that I can get my answer right here, because it must be giving me a quadrant 2 answer. Because this is a negative value, inverse cosine of a negative value must give me a quadrant 2 answer. Okay, so this is easy to figure out because, again, remember this is pi. I'm just going to be doing pi minus 2 pi over 9 so that I can figure out the main angle here. Don't forget this is 9 pi over 9. So final answer is going to be 7 pi over 9. So therefore, the arc cosine of cosine 11 pi over 9 is actually equal to 7 pi over 9. That's my solution. Okay, last one here. I'm going to be doing the secant of the inverse tangent of 8 over x. And by the way, for most of these, what they go ahead and tell you is that x is a positive number. Okay? I don't actually need to qualify that on this one, but I'm going to go ahead and just do it for the sake of argument here. So remember, what this is saying is this inverse tangent is going to give out some angle. Okay? So let's call that angle something. Right here, this inverse tangent is related to some angle. I'll call it gamma. Okay? So angle gamma, and it's going to be an inverse tangent of a positive number because 8 is positive and x, we said, was positive. Okay? So that means that gamma must exist in quadrant 1. Since I'm doing the inverse tangent of a positive number, remember inverse tangent only does quadrants 4 and 1. And when it's positive, it's a quadrant 1 answer. Okay, so what does that mean? It means that from this piece of information, I can insinuate that whatever gamma is, whatever it is, it's an angle, and whatever it measures, the tangent of that angle is equal to 8 over x. Whatever it is, it's going to have to be that to make sense with the way we're equating it there. And so what this further implies, okay, then all we need to find is secant of gamma is our answer. Okay? So let's start out by drawing it up. In quadrant 1, I'll have some angle, gamma. And if I set up the triangle for this, right, this is the x and y point right here. Tangent is opposite over adjacent. So that means this must be 8, this must be x. And therefore, I can figure out the hypotenuse by doing x squared plus 8 squared and square root it. In other words, Pythagorean theorem would be x squared plus 8 squared is equal to, I'll use little c squared since that's typically the hypotenuse there, right? Could also use r. Sometimes r is for the radius of something. Notice all I want is this c to be solved for. So I'm just going to square root both sides. Well, instead of 8 squared, I'll go ahead and write out that's 64. And I can't do anything else with that, right? Because of the addition, I can't split that radical. So this is going to be square root of x squared plus 64. And now I have my triangle. Therefore, I can just write out my answer now. The secant of the inverse tangent of 8 over x is equal to, well, what's the secant here, right? Secant is reciprocal of cosine, so it's going to be hypotenuse over adjacent. In other words, it's going to be the square root of x squared plus 64 over x. So let's finish up this test with these two application problems. I have a boat that leaves a port and travels 47 miles north, then turns east and travels another 78 miles from there. Okay, so then what distance afterwards and what cardinal bearing would it be for the boat to travel back to the port? Now this is important, don't forget. It matters which way you're looking for the cardinal bearing, right? Is it from the boat to the tower, or is it from the tower to the boat, or port to the boat, or boat to the port, right? In our case, we're going to be from the boat back to the port for the bearing there. With all of these problems, it's best to just draw it out and to have that picture to go on. Okay, so let's do that. I'm going to draw the port at some point, like so. And at this port, I'm going to put a north-south line and an east-west line. Okay, so here's my north line, here's my south, here's my east, and here's my west, and the port is in the center here. Okay, it was said that the boat traveled 78 miles east, but after we did the 47 miles north. So he traveled north first, right? He traveled north 48 miles. Not 48, 47 miles. 47 miles north. Then, from this point, he traveled due east 78 miles. So right now, this is where the boat is, right? The boat is right here. So then we want to know what's the distance and the bearing of this line right here, right? I'm looking for this distance. And don't forget, this is a right angle because north and east are defined as being perpendicular to each other. Okay? The best thing to do here for this is to, for the bearing anyway, is to draw another set of north, south, east, west lines. From the boat, this is north, right? And here's east, right? South, west. And of course, the two eastern lines here, the two east-west lines are parallel with each other here, right? And so are the two north lines are both parallel there as well. Okay, so the distance is pretty straightforward. I have a right triangle here. I can just use Pythagorean theorem to find the distance. Okay, this distance right here is simply the square root of 47 squared plus 78 squared. Okay, so this is just a power punch, right? A punch and crunch. My handy dandy time saver. Square root 47 squared plus 78 squared. I have 91.06. So let's just say 91.1 miles. Okay? Now what about the bearing? The bearing is based on this angle right here. We'll call it theta. This angle right here, because from the boat, right, the boat must travel from the boat, I could be facing south, and then how much do I rotate west to get to the direction of the port? Okay, so I'm interested in this angle here. However, that angle is not in my triangle over here. I can just use a lot of parallel information here. Okay? So, since these two east lines are parallel and these two north-south lines are parallel, okay, notice this is parallel with this. This line right here, BP, would be a transversal. And that means that this angle right here would also be equal to theta as an alternate interior angle. Or if you want to look at it like a rectangle, right? This is a rectangle right here. This would be 78, this would be 48, and you could have a right triangle over here. It'd be the same orientation. Regardless, this now shows me that I can compute my theta angle using the right triangle here by saying that the tangent of the theta that I'm interested in, opposite over adjacent, is 78 over 47. Therefore, my theta is the inverse tangent of 78 over 47, which I again have to punch up in my handy dandy time saver here. Inverse tangent 78 over 47 is 58.93. Let's just say 58.9 degrees. So theta is approximately 58.9 degrees. That's not the answer. Remember, the angle in this case is not the final answer. I need to give a bearing. So we're going to travel 91.1 miles at a bearing of south 58.9 degrees west, because we're facing south and rotating to the west so that the boat can travel along this line here. Okay, so that's the other portion of the answer there. Okay, next I have a weight on a spring that is being oscillated. It's following some simple harmonic motion here. So, okay, here's what's happening. After being pulled horizontally from equilibrium, a weight on a spring follows this simple motion. Okay? So in other words, the weight must be attached to a spring which is attached to something rigid. Okay, so imagine, you have some sort of brick on a wall or something like this, and you have this spring, right, attached to some sort of weight. It's being pulled initially to stretch the spring out, and then it's let go, and then the weight wants to do this, back and forth, back and forth, back and forth. Okay, so I'm imagining that it's on some sort of smooth surface here, right, connected so that it can just slide back and forth on the spring. Okay, so it's simple harmonic motion if we say that the weight never speeds up or slows down after you release it. Or I shouldn't say speed up and slow down, because technically it's speeding up and slowing down all the time. I mean, it never loses energy or gains energy such that the distance maximums never change. Okay, so in other words, the weight got stretched. When it lets go, it compresses the spring to a certain amount, and then that wants to push it back out, and then it wants to pull it back in, and then push it back out. And if it's simple harmonic motion, then the distance that it travels on either side of the middle equilibrium where it used to rest is going to stay the same on both sides. And that's actually the first question. What is the maximum displacement? Okay, so remember, the weight is doing this. It's being stretched to here, and then it's bouncing back and forth, right, between these two. And this original equilibrium, right, equilibrium is in the middle there. Well, the maximum displacement is going to be this distance here. In other words, the amplitude. That's 3. And of course, it's measured in centimeters. 3 centimeters. Okay. What is the period of the motion? This is just like the graphs that we're doing, right? I can compute the period by looking at the B number here, right? We sometimes call it the frequency, but in this case, I'm not going to call it that, because the frequency has a separate definition, because there's an actual frequency of the motion that has nothing to do with the frequency that we were using for graphs in this case, okay? So what is the period of the motion? Start there. Remember, the period is 2 pi divided by B. So divided by pi over 4. I'm going to reciprocal multiply here. So 4 over pi. I'm getting 8. Now, remember the units of the period. This is important. The period is the length of a cycle. Okay? It's how many seconds it takes to finish a cycle in this case, because t is my input variable, right? So how many seconds does it take? How long across the axis? It's the time axis. How long on the axis? That would be 8 seconds per cycle. That's the units of the period, seconds per cycle in this case. Okay, next, what is the frequency? Well, remember, the frequency, the one that's defined for this kind of motion, is the reciprocal of the period. Okay? Frequency is the reciprocal of the period here. Sometimes we use F. Sometimes they use the rounded Greek omega that looks like a W, but it's real curvy. Okay? We can use F. That's fine. It's the reciprocal of this. So what do we get? 1 over 8. And what are the units? Reciprocal. That would be cycles per second. Cycles per second. How many cycles fit in a second? In this case, 1/8 of a cycle. It's a very, very slow oscillation. It's taking 8 whole seconds to complete one big long motion. 1, 2, 3, 4, 5, 6, 7, 8, right? So it's like 1, 2, 3, 4, 5, 6, 7, 8. Like that. That takes 8 seconds. That's slow. So 1/8 of a cycle fits in a whole second. Okay? So D, where is the weight at 5 seconds after release? So you stretch it, we release, count to 5 seconds. Where is this weight located? Well, what I'm going to do is I'm going to take 5 and plug it in to T. Let's do that. So I have that D displacement is equal to -3 times cosine of pi over 4 times 5. This particular part of it is just a punch and crunch. Right? Got my handy dandy time saver. -3 cosine. Be careful. Needs to be in radians. This is a real world connection with sine and cosine. It doesn't have anything to do with angles. Use radians. That's the natural connection. pi over 4 times 5. I have 2.12, and an important thing to note here is that it's positive. So this is approximately 2.12. Okay? Now, we have to describe this. 2.12 is not enough to answer this question and wants to know where it's located. Okay? So there's a couple of little details here. Remember, we said that it was stretched this way to begin with, and it begins with a negative peak. Okay? Because it's cosine. Remember, cosine starts on a peak. But here we're starting on a negative peak. So in other words, we're counting this side as negative of the equilibrium and this side as positive of the equilibrium. Well, we got a positive number here. So we are 2.12 centimeters to the right of equilibrium. That's how you would describe where the weight is at the 5-second marker. Not after 5 seconds, right on that 5-second mark. That's where it'll be located. Okay? When will the weight be in the equilibrium position for the first time after release? So I stretch it out, I release. When exactly? How much time passes before it hits that equilibrium? Well, this is a cosine, remember? Since it's a negative cosine, okay, remember, a negative cosine graph did this, right? Remember when we were graphing it? And if you break it into the quarters, you have this break, and this break right here. So it goes up to the middle, then it goes up to the peak, then down to the middle and down to the bottom. Well, what it's asking is, when is the first time that it hits that equilibrium point? Well, that would be after the first quarter period. Remember, we're doing everything in quarter periods? So the first quarter period for a cosine hits the center line again. Well, that's all I need to look at. What's the quarter period here? My whole period is 8. Well, my quarter period is 1/4 times 8, which is 2 seconds. And that's actually the answer. Because it's the first quarter period, right? If time 0 is here, that's t equals 0, then when does it hit this equilibrium? That's a quarter period right there. Here's the next quarter, here's the third quarter, here's the last one, right? This is going to be t equals 2, 4, 6, and 8 for a full period. So t equals 2 is the first time it hits that equilibrium. 2 seconds is the answer there to this. Okay? So I hope this whole string of test problems helps you in your endeavor to study for your own test in your trigonometry class on this particular unit.